Excuse me. Excuse me. All right, I'm going to open up a presentation now in AFNI handouts that I believe is AFNI 42. Yes, about it's called QC project. So it's AFNI 42 for Hitchhiker's Guide to the Universe, folks. This will obviously be the answer to all the universe of processing. All right. So we've talked a little bit about aspects of a lot of processing and then also quality control. We haven't really defined quality control, and I feel like in the field it often isn't really well defined. It's kind of a vague concept where people say, well, yeah, I did data quality control, and they move on in their paper. It's not really given a lot of time or ink. Um, Sometimes we talk about it like, well, I'm trying to find the good subjects in my data, or I'm just trying to get rid of the bad subjects and drop them out. Um, that's kind of an aspect of it, but I don't think that's really what we should be getting at or what it really is in a deep way. It's, in our view, something that's really a much more holistic process. And I think Rick put it quite well this morning. You're doing a data study, it's your data, you're publishing results. You want to be as sure as possible that the results that you're putting out there and your interpretations are based on valid things, good data, that there aren't artifacts lurking there, and that you've done, everything possible to be sure about that. And that includes the raw data through every step running well, through the modeling and things like that, having an appropriate model and checking all these things. And this is why when we look at processing, when we talk about things, we've really tried to stress that you don't just do a step and move on. You do a step, you check it, and that really the check is part of the processing. Running AFNIPROC is not your full processing. You also look at the HTML, you run GenSS review table, you look at things as you go, even before you start. You always check alignment, etc. And so things that should be included when we think about whatever quality control is in this is you want to check data from the beginning through the end, through all your processing steps and be sure about things. And also processing, not just that a step completed correctly or it didn't crash, but that sometimes processing kind of opens up or gives you new angles that you might see features that you didn't know something was lurking there. While we're doing this, we really want to avoid bad things like wasting data. So just getting rid of all our subjects or something, especially when we're acquiring clinical patient populations, there's a lot of, valuable time of the participants that gone into it and may have clinical outcomes and things. We don't want to bias results by how we're getting rid of subjects or including them. And we don't want to leave QC until it's too late. That means don't acquire 200 subjects and then realize, whoops, my voxel size was 10 by 10 by 10, or I had this artifact in there, or I didn't include enough stimulus events, things like that. So piloting data is really key. So I want to just to motivate this a little bit. So, I'm going to give us some data and let's think about this. So is the following EPI data, fMRI data, good or bad? It has a high average TSNR, very high, and only 2 out of 150 time points were motion censored away. So, maybe from just this quantitative check here, people don't like qualitative. They say, well, humans are biased and all this. So from these numbers, sure, our data is good. And maybe some people would call it a day. Let's dig a little deeper and maybe look at a slice of the raw data. We say, okay, great. And now I can move on. Well, what about if we look at a montage of slices more systematically? This really shows us that some local feature actually might be quite problematic, in this case, severe signal loss. And this data set is probably not very good, right? So now we might exclude this subject. Well, here's a question though. What if our study was specifically about the visual cortex or the motor cortices, which are here and not in the problem zone? Well, maybe this data is actually usable and it would be a waste to throw it away for this particular study. Life with data is complicated and we can't just say, is data good? Is data bad? We have to tie in these questions to our specific study. And, you know, life is hard with data. We're trying to study the brain. What should we expect? Okay, but let's try again now. What about this data that has even higher TSNR and only 7 time points of sensor data, a few more, but really high TSNR? Well, this is good, but maybe we've learned by now that we don't just want to stop with the simple quantities here. Let's look at a whole montage, and okay, now we're happy with the data, so we're going to process, and we don't have to look at our data ever again. Great. Well, okay, what if we looked at a seed correlation map, a seed-based correlation map in the PCC, and we see this kind of correlation pattern when we actually look at our data after processing? This is pretty bad. You may be new to resting state processing, but this is not a biologically feasible pattern for correlation. It goes through gray and white in these weird slabs and things like that. Um, and this is why, fMRI data is not just time series averaging. It's not just spatial, it's four-dimensional. There's both space and time. And so we've come to really appreciate spatial temporal properties as key. Hence, we've emphasized Instacore a bit earlier. And that's why our quality control actually contains images like this and gives you Instacore at your fingertips to check these things. Okay, so motivated by these questions, what is quality control? And there isn't a lot of this information or education in the field. A few of us in the core and Joe Etzel at Wash U, and with Arshita and Dustin, the DSST, we put together this quality control project where we wanted to invite basically teams of anyone who does analysis and especially methods groups to put together their own quality control manuals with a lot of examples, essentially. And so what we did is we got some real data from a lot of different public sites where nothing was changed, and we just asked these teams to quality control it and write in detail what they were checking for and what they found. And the goals of this were to basically put out there um, more tutorials and more information for new people in the field, for old people in the field, frankly, about different tools and what quality control checks existed. And we were really happy that so many different tools and developers across a lot of different softwares participated so that users of all these tools can really have more tutorials and information at their fingertips. We wanted to have people put out a lot more examples for new people in the field to share ideas across researchers and developers. We certainly learned a lot about quality control and the way people look at it and think about it, and forcing ourselves to think deeper and make things easier to check. And then also to kind of put out this idea that quality control is not just good or bad data, but it's understanding your data. And if you just get rid of bad subjects or what you call bad subjects and don't dig deeper, you might just leave systematic artifacts or bad things that you keep acquiring, and you don't really understand why it's happening to fix it and improve things for more. And Lord knows the field talks about reproducibility a lot. I don't know why no one ever mentioned data quality as an issue for reproducibility, but certainly it is. And I think this project really brings that home quite a lot as well. So we asked teams to go through both real and task data that we collected and to categorize every subject as either one that you would include for a general whole brain study with high confidence or exclude, or if you were uncertain and why. And there were a lot of uncertainty. We really learned that there's a lot more that we need to understand about quality. This was actually a large category. And each team we asked to like put list item by item their qualitative and quantitative criteria, and then to make a lot of examples in their paper about what they did to basically make a manual about this. And so the data we used, there was from Abide, the Functional Connectome Project, and a lot of open neuro data sets, about 20 subjects from each, focusing on kind of very standard 3 Tesla data, really just kind of like bread and butter data that the field has been using for a long time now. And again, nothing was changed in the data. There were no gotchas, no little tricks or anything. This is all just real data. We had 10 different teams participate, including our team, and then again, lots of different software, and it was really encouraging to see how many groups really care deeply about this topic. And to give you a sense of all the different software that were used, there was a lot used for processing and also for quality control. And so it's nice to see that a lot of different tools and developers have also been thinking about this and trying to put tools at the user's fingertips too. And just to give you a sense of all the different ways you can look at your data and people think about it, there's really just an amazing set of things across all the tools and papers. And I encourage you to look at all the papers, regardless of what software you use. And just as kind of a summary thing, so for four groups of data, so four different sites essentially, the A, B, C, D are each different team that was rating it. Gray meant a team didn't choose to analyze that, and these row by row are the subjects. If you see red or orange, it meant that a team decided that a subject should be excluded. A couple different take homes from this. One thing is just by the amount of red that's here. Again, this was data that I will say that I purposefully tried to avoid really pathologically bad data. I tried to get data that was reasonable from just a quick visualization. And there were a lot of very bad data sets I did not pick. But even so, many teams excluded more than 25% of these subjects. And so if you think about, oh, I don't need to do quality control, think again because every data set, every um, that you're collecting or downloading really needs a check. There is heterogeneity across groups. Some groups, like G, excluded basically everyone or almost everyone. Some sites had some that they were uncertain about, some that were more droppy, some excluded very few. And it's interesting. I'm not someone who thinks that the heterogeneity of this is really like a panic moment for the field, but I do think that there will be more convergent evolution in ideas and the way people look at data. And it's interesting. One of the main things was, for example, what do people want to do about motion? Do they want to censor with strict thresholds? Do they want to leave it to group analysis and do something else? And that kind of heterogeneity of strategy was really apparent. And there are very consistent ways to do it through either of those branches of processing, but you have to be clear about what you're doing and why and make sure all your processing goes with it. And the latter four sites worth of data, it's a very similar story among these. So really the main thing here is do quality control because every site worth of data needs it. And just as some summary points, each team found subjects to exclude, often many and often very many. So please check all of the data you download or acquire for appropriateness. Each team had uncertain results, and this is really something that the field doesn't talk about in papers. You know, what do we do with these in-betweeners or something looks wrong, but I don't know what it is? And these are things that just mean that we need more quality control checks and to think about as a field. Um, I was really pleased that kind of every group was also looking at raw data consistency, something that we find important. I never see written about in papers, but this is something that should be emphasized more and more. And also, each team identified some kind of inconsistency or reliability problem or mismatch. There were two upside down brains in data. I will say that again, two upside down sets of data. So this means that people who uploaded it didn't run some basic checks or the software they were using didn't check for things. These are things that really we want to check for. We also found left-right flips, and our team kind of found, as I mentioned, this mismatch between an anatomical and EPI. I think another group using AFNI did too. Um, Every team used qualitative criteria and visual checks. These were kind of the heart of everyone's QC. Most of them, but not all of them, also had quantitative or automatic command line checkable checks. QC parameters, a lot of teams emphasize that you really, it's hard to say in general, is this good or bad? Because you really have to add some specificity to it. And so you really have to define your study goal. So something that may be good for my study may not be good for your study or vice versa. So we always have to do QC, even if I know what you found in your QC can inform me. More than just EPI data are important to check, like the quality of your anatomical, are the timing files information correct, etc. And what's really nice is everyone made their both pipelines and QC public, so you can go to the papers and see where they are on OSF and GitHub and things like that. So it's really meant to be educational. So thanks to everyone who participated in it, both organizing and doing the QC, all the reviewers and things like that. Um, Now Daniel is going to guide us through looking at some of the data of the QC project from some of these different sites, and in particular, looking at it with AFNI-Proc for what we can learn using it. So take it away, Daniel.
Thank you. Okay, I have to replace the current share.
Okay.
Share it.
Yeah, I don't think I can't. Okay, thank you.
I
Yeah,
think I got it.
good. Okay.
Um, Move things around here. So, so I'm going to start with this presentation in the AFNI handouts, AFNI 43, the next one. So maybe chat. You can just watch it too. So there. Why is that? Okay. All right. So let's get started with this full screen. Okay, so we're going to look at the way we did this project, and there were all these different groups, but we did it our particular way. So let's look to see how we've done it. And so, as Paul said, we look at the good, the bad, and the other, and we do that by looking at things like the consistency of the data sets, see how uniform they are across all the different inputs. We want to see if the processing steps are successful. So that's a little different than what QC has traditionally been thought of in our field, where it was usually just looked at as quality assurance at the beginning as acquisition. And so we're looking at the processing as part of this whole thing. So everything that you do to your data, are you doing it? Is it correct for this kind of data? Is the data correct for your processing steps? And is the data suitable for your study? That's another part of this. So we want to make sure that this data is good and the analysis is correct for what we're going to say for it. All right, so we recommend using AFNI-Proc because it includes all these quality control steps. You can do analysis with other things. You can also do analysis of non-fMRI processing with AFNI. We don't have this kind of automated quality control, but we do include quality control at in various steps, like alignment. So and those are things that you should use and think about in all the kinds of processing that you do. Okay, so we divided up quality control into these different stages. And the first one is the getting to know your data. Okay, so here this is basically what we do when we receive data from all of our users is we look at the data in terms of the header to see, does it make sense? Can we look at it? Are they consistent? And we very often find problems. And traditionally, we've used our basic tools of 3D Info and Nifty Tool and 3D Brickstat. But now we have tools that will simplify this with getting to know your data check.py and GenSS review table. So this is an output from getting to know your data check. So you give it a bunch of EPI data. So if you have 100 or 1,000 or whatever, you can feed it into getting to know your data check, and it will give you tables like this. You can load them into a spreadsheet program and see what they look like this. You can so here, for example, this is real data from that project, and we have the number of voxels in each dimension, an IJK. And so we can see that, for this particular site, well, some of them were 128 by 128 by 34 slices, uh, uh, but others were 80 by 80. And the voxel resolutions kind of matched that too. And so these kinds of things will be very different across your subjects. If they're different, how are you going to be able to compare your different subjects? So you have to look at these things, and this is a problem that happens all the time. You can see the obliquity is very different for one of the data sets. One is much more oblique than the other. Will we have to process that differently? Will the alignment be different because of that? Sometimes we see the TRs are different. So there are things that we need to be concerned with, and there are many other fields that the getting to know your data check looks at nowadays. Okay. Um, with the results of that, or from AFNIPROC.py, you can also take the use GenSS review table and look for outliers. Paul has spent some time talking about how you can look at different kinds of outliers and make a special report that just shows you the outliers. Okay. And so that was mostly about just the input data. So you get data from a repository, you get data from a colleague, you get a whole set of new data that you haven't seen before. How can you look at it just to start? And that's one way to do that. That's without processing. Now, the next step is to look at the processing and see how did it go, right? So was there motion? Uh, do we need to censor were there outliers? How is the global correlation, the G-core, match up, and the TSNR? So is that at the level that you want it to be? So and again, we'll use GenSS review table to extract outliers and see that things have gone wrong across any of our subjects. Here's an example using including the processing part of this. So it gives us we can look at the degrees of freedom, we can look at the censoring, we can look at the global correlation. These are just examples for this presentation. For your data, you will probably use something different. Um, okay, so and this is the output from that. We get this handful of subjects that didn't make it through that quality control test, and says, okay, these are the ones that we might want to reject or take a look at some more. Okay. Now, even if we can quantify it, even if we can see about consistency, we still need to look at our data. This is kind of the mantra of AFNI is look at your data. So we try to give you different ways to look at it. And so we're going to do this in the one way is with this qualitative review. And this can be in the form of these HTML reports that you've seen some of. And we use this openapqc.py to open up these HTML reports. And we'll go through some specific examples here from this quality control project. Now, even if you've done this particular summary report of the HTML, you still want to look at it in depth. And we will. So this is more about the quality control. This is how to use the command. We'll go through one of these. Oh, yeah, we'll go through kind of overview of this first here. Okay, so this is these are some examples from this project. And so you can see that there are different things that we saw from across the different subjects. So we found things like this kind of strange artifact here. Is this real or not? There's a dropout region there. We have very bright CSF and larger ventricles. We have possibly some eye artifacts here. we have this kind of artifact, this kind of ghosting and art, this distortion artifact here and here. And so things like this led us to exclude this subject. In this one, we have this kind of familiar striping pattern. Uh, uh, in this case, we thought it was kind of limited, and we didn't exclude it. We just left it as uncertain. So this yellowish orange is this uncertain rating, and the red we've excluded it. Here, this is very large ventricles, and we did not exclude it, but it is something to keep in mind. And why would we exclude large ventricles? And a lot of other groups also excluded large ventricles, because you look at it and you say, well, this is really unusual. And the reason to exclude it may be that alignment will not work as well, because alignment is made to make, aligning to a template is made to work with uh, subjects that are close to that template. The ventricles, if at this size, might make that difficult. So you'd have to go through it and check to see if alignment worked properly, and maybe it will work for part of this. So if we sometimes deal with even worse problems like hemispherectomies, where distortion is even worse, and we can find some workarounds, but things can be very difficult if you have these kinds of problems. Oops. So and then we finally have this one down here. This is the one that Paul mentioned. So this is one that's an upside down brain. So somehow this escaped everybody that distributed this. So and we found not just one, we found two of these. So that's I think probably people have pipelines that assume some kind of orientation, and they moved these around. I'm not really sure what they did to get to make this work. Okay. The we also have these kinds of seed-based correlation. This is the default mode network, and as you look at them across different subjects, you'll see what normal looks like and what abnormal looks like. So the top one, this is what we would consider a normal result for a default mode network. And then if we go down here, this is not normal. Okay, so we've put something in about this in the same seed region, and we get this kind of result. So we got very high correlations, and if we're doing resting state, correlation is all we've got. So this is polluting all of our results. So there's not much we can do with this kind of data. And then we get things that are kind of in between. We have this very noisy pattern. It's sort of like default mode network, but it's not as clean as this, and so it's concerning. But we can't exclude it. But maybe we'll take a look at it again and see what the problem is. And then we have ones that have very, very low correlation. Were they asleep? Was there something else going on? So different things to think about. Just like default mode network, we can have a visual network. So this is a different seed. And again, are we seeing this kind of network, or are we seeing these non-physiological artifacts? Are we seeing low correlations, or are we seeing very, very high correlations, but they're everywhere? And then this is just looks at the overall correlation. How correlated is the brain with the error time series altogether, the average error time series. And so you can see that this is what's normal. So cortical regions generally show up together, but not the whole brain. This is way too correlated. Why do we still have this correlation? This is after regression, after motion correction, we still have this high correlation. So all of these have too high correlation and in somewhat different ways. Okay. So this radial correlation, we already knew that it was a good tool, but this turned out to be a very, very handy tool uh, for much of what we were doing. This found a lot of surprising results, and it was made for this kind of thing. Um, radial correlation, radial correlate, done with the program at radial correlate, is a tool that looks at correlation in a neighborhood, a spherical neighborhood at a time. And so it moves around the whole volume and it says how correlated is the this voxel with its neighbors. If you see large regions that are correlated all together, that's an indication that something has gone wrong because the region is large enough that we don't expect that kind of large scale correlation. So so here this is kind of normal, but down here we have this kind of abnormal pattern. So very high correlation. This ended up being a very important tool to look at all these different subjects. Now, this is the classic TSNR, and I say classic because everyone uses the word TSNR, and everybody thinks they know knows what it means, but every different software package has it defined slightly differently. Well, sometimes dramatically differently, and so that's kind of surprising. So you have to say actually when at what stage in the processing and how you've computed it. So we do it a certain way that is in our proc script. Uh, and others may not do it that way. So TSNR is a term that it should be defined better when you use it. So here we're using it after regression. So this is on our regress time series. If you look at it before, you get different kinds of numbers. So it's the temporal signal to noise ratio, and it's everyone agrees um, that it's a ratio, it's signal to noise, but what the signal is and what the noise is means something different for every different package and at every different stage of the processing. Okay, but we're going to use it this one way. And so here's what we typically see on a good subject. Uh, so it's generally, in the brain, it's mostly uniform. But in here, we'll see this kinds of things that we've mentioned a couple times now during this boot camp. So we'll see lower TSNR in these inferior regions, sometimes in the temporal lobes, and often in the cerebellum if it's acquired at all. Which in here we only acquired a little piece of it. And here this is the problem that we noted. This has this kind of vertical stripe of low TSNR. And then when we looked at it further in using Instacore, we noticed these big patterns of correlation that are not physiological, and we ended up switching it from not certain to exclude. So looking at this can give you some clues as to what things can go wrong. And that led us to searching for these variance lines. And now we have the variance lines and we have the variance maps in our HTML reports. And so this is a very useful tool now that came as a result of this project to find this. And I will say that we found this in lots of data sets. We've collected more and more of these kinds of things, and we find it again and again. It's probably, I think Paul has looked at but thousands of data sets from different sites, and maybe 10 to 20% of the sites have this problem. Sometimes, sometimes in all the data. Another thing that affects a lot of people's data are these left-right flips. Sometimes it's all the data from a site. Sometimes it's just a few. In these that we looked at, it was just in just a few of them, but it's still a very important problem. So we found this some years ago with the help of an AFNI user who said, "Hey, this looks like it's flipped," and then we quantified that and we made it part of our quality control and the alignment procedure. So we can check to see if the data is consistent between left and right, between the EPI and the anatomical. It doesn't say which one is correct. It just says if it's consistent. So if we find that the flipped data aligns better than the unflipped data, like I said, that's suspicious. It shouldn't be. And so this is an example here of the cost function. So the cost function is lower on the flipped value, and we can look at the alignment and say, ah, here, this alignment looks much better than this alignment. So the flipped data is better. So that means that the orientation is not set correctly in the original data. So this happens. There are lots of ways it can happen. So you need to, if you're getting data from somewhere else, you really should check for this. And I'm happy to say that most of the other software packages are now doing this too. So um, now, so even with all these HTML pages, we still encourage you to go into the AFNI GUI or the Summa GUI too, and use things like Instacore. So that is, we want this for a deep dive into the visualization. We've spent some time on how to look at data. This is uh, the HTML pages give you a nice quick way to look at a lot of data, but if you're doing your own study, particularly, you need to go in and look at it in detail. You need to look at the graphs. You need to do Instacore. Many of our users now say that they won't uh, uh, do anything without Instacore anymore. And this was kind of the result of this QC project, is that it really showed how useful Instacore was. And so using Instacore, normally we would see you'd click in one place and then you would see these kinds of correlations, kind of limited correlation just to the areas around it, uh, not too much farther. But in lots of other data, we would see these kinds of patterns. So you'd click in the image, and then you get these kinds of patterns far away, physiologically not reliable, not believable. And and so we said, okay, for these subjects, these were all excluded in this project. And and you can kind of see this kind of thing if you go into Instacore. This is sometimes what we see. This is not one of the quality control projects, but we'll see that strange artifacts like this can happen. And this will show up with the radio correlate output and oops, and with this Instacore kind of analysis. And so this is where you would go open up the graphs, and you could see that at some point all the signal would drop. Some connection would be lost there. Very often what we find, even at NIH, where they do quality control all the time, is that a coil will eventually go bad. It flexes a little bit, and over time, it loses its connection, and you may lose a month, 2 months, 3 months of data if you don't see this quickly enough. So you have to keep looking at this kind of thing. Even if it's good at one point in time, you have to go back and look in detail. Okay. For the task stimulus, you still have to do some even more stuff. You need to look at the motion to see if it's correlated with the stimulus. Is there stimulus based correlation with the motion? Uh, are the participants responding? Are they compliant with your task? Are they asleep? So you need to look at that in the results. Are you getting the levels of output that you want from simple visual stimuli, simple somatosensory kind of stimuli, those kinds of things. So here's an example where we think that there's some motion correlated uh, uh, data, excuse me. So that's so we're seeing the task and the motion together. All right. And we have other kinds of output. You've seen the gray plots, you've seen the motion plots. These are all things that you need to look at and to see, are they what you expect? Are you getting very large changes? Are they moving throughout? This is motion is the biggest problem that we see in almost everybody's study. And so you have to see, is it too much for your analysis? Okay, so we went over some of these things. I don't even really have any time, but I'm gonna exit out of this and see if I can find it. Okay, so in uh in the directory that this one, so yes, CD to bootcamp QC sub rest A, you can see some of the data that we looked at. And so we have a couple examples here. So that's from the home directory. And we in this directory, we have uh, do open APQC. I'll just show you what that contains. And that has just one line, really, that tells you the program to go find all the index files that are in this subdirectory and down. Okay. So if I do that, I can do tcsh do. So and this should open up Firefox and opens up all of our of the data that we want to look at. So we're just going to look at these four data sets in this part. And so we've got subject 115, 206, 417, and 516. I'm going to go over to 115 and we'll take a quick look at that and see what's wrong. Now, I can see right away that the warns button is red, so that's not good. So we can go down and find what's going on with that. But let's go through each of the sections uh, and see what it's got to say about that. So so we're looking at this CSF and just to the thought process of how we're going to review this. So I look at it and I see the CSF is kind of bright, but this is a pretty good data set here. The variance, I don't see any variance lines. I don't see anything very strong here. Skull stripping was roughly okay. It's a little bit severe on this, but this is oblique data. Now it's oblique data, but it's still it well, it's not really, it's not oblique data. I'm sorry. This is before any oblique processing, but it still matches, but it doesn't match exactly, so that's kind of suspicious. Um, and that'll come up later. And uh, and then I'll look at the alignment of the EPI. Oops. So the alignment of the EPI shows this is, after alignment, I would expect it to be a little bit better. So it's a little bit off on this side, even just by the contours, and it's a little bit out here. Um, it's not too great, so that's suspicious. But the alignment to the template of the anatomy looks pretty good, and the mask is uh, kind of okay. It's off on one side, so the EPI mask is a bit strange, but it's close to okay. And the correlation maps look fine. This is a little bit higher than what we'd usually see, but it's still fine. We do have this kind of thing where we have the motion. We have motion right at the beginning. So that's kind of unusual. Is it really motion? Um, and we have only one other motion event further down. So it looks like someone moved a bit left to right at the beginning. And it's the gray plot, which doesn't look so unusual here. So it really not it doesn't reveal too much to us. Um, Degrees of freedom, 80 remaining 84%, it's fine. Uh, and the correlated the measure of correlation, the core brain output looks okay. And the TSNRs uh, look fine. And then we have this report that has the depth like here. So the nucleus accumbens is very, very small, and we will almost always get this showing up. It's relatively small for fMRI. So so we will get that often. But if we were interested in the nucleus accumbens, and many people are, then we'd be a little bit suspicious of some of these results. The TSNR is a little low for one of these regions and slightly low at the other quartiles on others, but mostly this is okay. Radio correlation is high before motion correction, but after motion correction, it's fine. So that's fine. We're not getting any other warnings there except that this warning about pre-steady state. So AFNI-Proc will check to see if you may have left some pre-steady state because it checks to see if there are outliers in the early part of your data. It says, well, there are, but we already know from the motion plots that there was motion right at the beginning and that we seem to have corrected it. And that will drive this kind of the early correlation that we saw before motion correction. And finally, we see that the left-right flip is the only remaining severe warning. And this shows us that our flipped value was lower when the flipping gave us better alignment. So if we look at this, the original is a worse match than the flipped version. So this is how we find the data is flipped. And so because of that, and because we don't know what direction to flip it back, because it's just an inconsistency between the anatomy, we excluded this particular subject. There are some variance lines, but they're right at the front of the head, and because they're right at the limits, we generally don't think that's a problem. And then we have the final report here. You've seen this now a couple times. This is we'll look to see all these values. and make sure that our TSNR, our global correlation, our motion are all okay, and they all are here. Okay, so that was the first subject, 115. Let's take a look at another one. Um, this one is uh, we'll go through this a little bit faster. This is looks like one that Paul showed. The variance pattern is pretty high. You can see the striping right there. We can see that the Warren's button is pink, so we'll probably see that further down too. Um, Other than that, uh, so this is without the obliquity, it doesn't align. And when we apply the obliquity transformation, it's in about the same place, but we'll see some dropout. So if we're interested in those regions, it won't work as well. Okay. I'm going to go through this a bit more quickly. Um, okay, so seed-based correlation. Everything here looks mostly okay. The correlations are a little bit weak on this. Um, and let me go down just that we have almost no motion here. So uh, correlated brain seems roughly all right. We have the low TSNR in the center, and we have various warnings for our different regions. And this is the radial correlation, which also seems okay, except it's over. There's too much correlation in the center of the brain here. And we don't have any flipping problem, but we do have this very strong variance line. So let's take a look at that. One of the best places to look at that is to go back to the original data, and which is at the we can get to that through the radial correlation. This will open up the data with this do correlation with the PB00, so a very early stage of the processing. Um, the earliest stage, just removing the pre-steady state. So we can click on the IC button. And you can kind of see right away that there's something suspicious. We're getting very high correlation, but we can click around. You can see, patterns like this are not physiological, and we don't expect to see this kind of pattern uh, this way and that way. So lots of things going on in here. Um, you can jump to a particular position. So if I jump to, say, I think minus 25, 10, 10, and then to apply, you can see this correlation is very, very high. We have both positive and negative correlations that go, through much of the brain. And because of that, we decided to remove this particular subject. And we removed this particular kind of problem happened for every subject in that site. So this is a big problem, and we see it again and again, even across other sites. So this helps us see it. Instacore is great for this. I'm going to close this. When you're finished doing this, you can close the AFNI GUI, and we can go to another here. So subject 417. And here Again, we'll see the same kinds of things. Um, Again, we'll have these variance lines. So we can go even right to that. We can also look at the warnings, see what it says about that. Just to go this faster. So you can see this has lots of variance lines in different parts of the brain. This is a different site. Let's see what radial correlate Instacore will show us there. We saw that it was very often in the front, so let's click over there. Yeah, see very strong correlations everywhere. Um, and so if we're looking at correlations, we're not expecting this kind of very strong responses. And this, if I click it just right, I can get this kind of stripy pattern that goes through much of the front of the head. We'll see this pattern. So these are non-physiological. So we will remove this from we'll exclude this subject. All right. Now let's go back to just not just one more here and this subject. Okay, so here, subject 516, we have the bright CSF. We have some dropout here. Um, we've seen some of this before. Is a little bit of distortion at the bottom. Alignment looks okay. We have, a fair amount of dropout, but it's not terrible. So we go through this and we can see the dropout in that. Uh, Default mode network looks okay. Seed-based correlation's a little bit high, but all right. Auditory is good. Motion seems fine. Whole brain correlation is a little high, but not too bad. TSNR looks fine. We have some regions again that just are not deep enough and low TSNR, but we've seen that again and again. Radio correlation also looks good. So overall, oh, we also have only one, and it's right at the back of the brain, so only one variance line, and everything else in our report looks fine. So this is a good subject. And the reason I show you this is because there are, in fact, good subjects. It's not completely good, but it's mostly good. So we're going to take that and that not all data is has problems. Sorry, they have some minor problems, and it might be okay for your analysis depending on which regions you're interested in. So we've gone over these four subjects. If we can go to this. Let me close these guys. Oops. And I will go to uh, rest B. And here, there's also another do open. So I'll do that. And here, now it's up to you as an exercise for you to look at these two subjects and see what you think about it. I'll give you, I don't know, 5 minutes, and then we'll hear what you have to say. You can put your answers, what do you think about that in the chat. So this is the B subject. Okay. I'm looking at the chat. I haven't looked at it for the past 45 minutes. So, okay. See if I can get to that. So I'm in Bootcamp QC sub rest B. Oh, see if I can put a tilde in front of that.
Daniel, there's a comment in the chat about an axial view. There's some missing part of the brain.
Okay, so where do you think this is in the axial view? Which axial view do you mean?
I guess which subject ID are we looking at? The 208?
Yeah, I'm not okay, so the other one is not showing up for me, which is odd.
Sometimes this happens, and again, it's something I don't know with the web browser module that the if you just restart it, sometimes it'll come back. Yeah.
Okay.
Sometimes the first one gets left off. There's a pause that you can put in, but that doesn't often help. I have not figured out what the browser is doing.
Okay. Maybe the Firefox is still
Yeah,
slow.
sometimes I quit Firefox and restart and let it refresh. And
So this should do it. Okay, it did come back. All right. So in the fMRI data or in API data or in the anatomical data? 171 sounds like a slice of anatomical data.
is it 17I or something?
Oh, maybe. Oh,
Yeah, I think that, yeah.
that looks okay to me. I mean, it's really I don't see that as I mean, it's in the this is the MNI space. Let me look over here. Um, yeah, so this data does have some distortion, so it has some bump outs and bump ins in the on the API data that you could kind of see on these outlines. So that may be what you're looking at. This is also some drop. This is a dropout region. So the API is dropping out here. And so you can kind of see that on this slice.
Maybe I usually find when the warns level is high, I would search for the warns personally.
Kind of we have a little bit moderate level of censoring. Okay, so no flipping. But we do have these variance lines, so that's probably what we should be looking at. So if I go back up to Radcore and then Instacore, oops. Oh, I didn't mean to click done. Just okay. So let me do it again. Okay, you can see right away that there's something bizarre going on. So this is another one where correlation is non-physiological, and if we click around, we can see these kinds of funny patterns of correlation. So that's the main thing that's wrong with this particular subject. Okay. Well, removal by ICA. I think Paul talked a little bit about that, right? Um, our we have looked a little bit at this, and we're finding that it doesn't actually improve this particular problem.
Yeah, and the other part of that is let's say you could remove this much variance from your data. The problem is a little bit in the same way of like, what's the problem with a tumor in the brain? It's so embedded and entangled with other things, you can't remove it and not remove other things at some level. And so if you remove all these patterns, you're removing a huge amount of variance that is going to affect everything else that you have anyway. So there's kind of no way to remove it cleanly. I guess I would say that because it's so extensive spatially and temporally.
Right. Okay. So, okay, so for the other subject, what do people have to say about that? So we've got some dropout, fair bit, but well, in here, uh, went back and but overall, this is a great subject. So this is a subject that we kept. So we think it's a good subject. So this is another example just to have confidence in your data. You take a look at it and see if you can find these kinds of problems. So overall, I just want to say that quality control is one of the most important things that we can do when we deal with data. Now we're looking at fMRI data and this EPI and anatomical data. We have to be concerned with all the data that goes into the analysis. This applies to physiological data, physio data, cardiac and respiratory kinds of input data, questionnaires, everything that you use for your analysis, you have to check. And we find problems on everything. So you just have to be very careful uh, and make sure that it's appropriate for your analysis. Okay. So I've gone way over in time here. Um, let's well, tomorrow morning, 9 o'clock US Eastern time, we'll restart. Um, we'll I forget what the next topic is, but uh, you're welcome. Um,
It's group
uh,
analysis followed by more group analysis with a healthy dose of more group analysis before we're done.
sounds a bit like a spam song, but
Yeah.
do you like some group analysis?
Bacon, eggs,
And group
and group
analysis
analysis. All right.
with Chen, Chen, and Chen.
Yeah. All right. We've
All
obviously
right.
reached 5 p.m. So, all right, I'm going to stop the recording.